Imagine taking something the size of our sun, an object so massive it could swallow 1,000,000 Earths, and crushing it down until it fits inside a sphere no bigger than our planet. Now imagine that inside this impossibly small object, matter has been squeezed so tightly that a single teaspoon weighs more than an elephant. The atoms you learned about in school, the ones with electrons orbiting a nucleus, those atoms no longer exist in there. They've been destroyed, crushed beyond recognition into something that doesn't behave like any solid, liquid, or gas you've ever encountered. This is what's inside a white dwarf, a dead star that should collapse but doesn't. And the reason it survives is one of the strangest things in all of physics. Before we go any further, if you find this kind of deep exploration fascinating, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with something you think you understand. A star dies. You've probably heard that phrase before. Stars are born, they burn for millions or billions of years, and eventually they die. It sounds simple, almost poetic, but what does it actually mean for a star to die? And more importantly, what does the corpse look like? Because when a star like our sun reaches the end of its life, it doesn't just vanish. It doesn't simply blink out of existence. It leaves something behind. And that something is one of the strangest, densest, most extreme objects in the entire universe. A white dwarf. But to understand what a white dwarf really is, to truly grasp what's happening inside one, you need to understand what it was before it became a white dwarf. You need to understand what a star actually is, not in some poetic sense, but physically. What is a star made of? What keeps it alive? And what happens when the thing that keeps it alive runs out? A star like our sun is, at its most basic level, a massive ball of gas, mostly hydrogen, some helium, and trace amounts of heavier elements. The sun contains about 330,000 times the mass of Earth. That's an almost incomprehensible amount of matter. If you could somehow scoop up the entire Earth, everything, every mountain, every ocean, every grain of sand, every building, every person, and put it on a cosmic scale, you would need to do that 330,000 times to equal the mass of the sun. All of that matter is being pulled inward by gravity. Every atom in the sun is gravitationally attracted to every other atom. The combined pull of all that mass creates an enormous inward force, trying to crush the sun down to the smallest possible size. If gravity were the only force at work, the sun would collapse in on itself almost instantly. It would shrink and shrink until all of its mass was compressed into an unimaginably small volume. But that doesn't happen. The sun doesn't collapse. It sits there, stable, enormous, radiating energy in every direction. Something is pushing back against gravity, and that something is heat. Deep in the core of the sun, temperatures reach about 27 million degrees Fahrenheit. At these temperatures, hydrogen atoms are moving so fast that they collide with each other and fuse together, forming helium. This process is nuclear fusion. It's the same basic reaction that powers a hydrogen bomb, except in the sun it happens continuously. Billions upon billions of reactions every second, releasing staggering amounts of energy. This energy heats the gas in the sun's interior, and hot gas exerts pressure. It pushes outward in every direction. This thermal pressure, this outward push from the heat of fusion, is what holds the sun up. It balances gravity. Gravity pulls inward. Thermal pressure pushes outward. And as long as these two forces are balanced, the star remains stable. This balance is called hydrostatic equilibrium, and every star you see in the night sky is in this state. It's a delicate balance, but it works beautifully. The star burns fuel in its core, generating heat, and that heat generates pressure that supports the star against gravitational collapse. The sun has been doing this for about 4.5 billion years, and it has enough hydrogen fuel to continue for roughly another 5 billion years. But here's the critical thing. The fuel is finite. There's a lot of it, yes, enough to last for billions of years, certainly, but there is a limit. The sun is converting about 600 million tons of hydrogen into helium every single second. Every second. And it's been doing this for 4.5 billion years. Over those billions of years, the core of the sun has been slowly filling up with helium. Helium is the ash of hydrogen fusion. It's the waste product. And it accumulates in the core like ash building up at the bottom of a furnace. For a star like the sun, this process unfolds over an almost unimaginably long time. But eventually, the hydrogen in the core runs low. When this happens, the core can no longer generate enough energy through hydrogen fusion to support itself against gravity. And this is where things start to change dramatically. Without sufficient hydrogen fusion in the core, thermal pressure drops. Gravity, which has been patiently waiting this entire time, begins to win. The core starts to contract, to compress, squeezed by the weight of all the material above it. As the core contracts, it heats up. This might seem counterintuitive. The star is running out of fuel, so you might expect it to cool down. But gravitational contraction converts gravitational potential energy into thermal energy. The core gets hotter as it shrinks, and this increasing temperature has an interesting effect. The hydrogen in a thin shell surrounding the core, hydrogen that wasn't hot enough to fuse before, now finds itself in conditions where fusion becomes possible. A shell of hydrogen surrounding the core ignites, burning outward like a ring of fire around the dead helium core. This shell burning actually produces more energy than the original core fusion did. The outer layers of the star, now receiving all this extra energy, begin to expand. The star swells enormously. For a star like the sun, it will expand outward, growing larger and larger until it becomes a red giant. The sun will eventually grow so large that it might engulf the orbits of Mercury and Venus. Earth might survive on the outer edge, but it will be scorched, lifeless, barely hanging on at the boundary of this swollen, dying star. Meanwhile, something remarkable is happening deep in the core. The helium that accumulated there over billions of years of hydrogen fusion is being compressed and heated by gravity. When the core temperature reaches about 180 million degrees Fahrenheit, something new begins. The helium nuclei, each containing 2 protons and 2 neutrons, start to fuse together. 3 helium nuclei combine to form a single carbon nucleus through a process called the triple alpha process. This is helium fusion, and it's the star's second act. A new source of energy, a new fuel to burn. In some cases, carbon nuclei can capture an additional helium nucleus to produce oxygen. So the products of helium fusion are primarily carbon and oxygen. The core is now converting helium into carbon and oxygen, and this fusion generates enough energy to temporarily stabilize the core against further gravitational collapse. But helium fusion is far less efficient than hydrogen fusion. The star burns through its helium much faster than it burned through its hydrogen. While hydrogen fusion lasted billions of years, helium fusion in a sun-like star lasts only about 100 million years or so, a fraction of the star's total lifetime. And when the helium runs out, the star faces the same problem again, but worse. The core is now made of carbon and oxygen. To fuse carbon or oxygen would require even higher temperatures, roughly 900 million degrees Fahrenheit or more. And here's the crucial point. A star with the mass of our sun cannot reach those temperatures. It simply doesn't have enough mass. The gravitational compression isn't strong enough to heat the core to the temperatures needed for carbon fusion. This is the moment when the star truly dies. Not with a dramatic explosion, not with some cataclysmic event, but with a quiet failure. The core simply cannot ignite the next stage of fusion. It has reached the end of what it can burn. The carbon and oxygen sitting in the core will never fuse. They are the final ash, the last product of nuclear burning that this star will ever produce. What happens next is violent in a different way. The outer layers of the star, the enormous bloated envelope of hydrogen and helium that expanded during the red giant phase, are no longer gravitationally bound to the core as tightly as they once were. Through a combination of radiation pressure, thermal pulses, and stellar winds, the star ejects its outer layers into space. This ejection isn't instantaneous. It happens over perhaps tens of thousands of years. A cosmic eye blink, but still a process rather than an event. The expelled gas expands outward, forming a beautiful glowing shell around the remaining core. This shell is called a planetary nebula, though it has nothing to do with planets. The name is a historical accident from early astronomers who thought these objects looked like planetary disks through their telescopes. But the ejection process itself deserves a closer look, because it's not a single clean event. It's messy and prolonged, and it happens in stages. During the final phase of a star's life, a phase astronomers call the asymptotic giant branch, the star becomes deeply unstable. The core is surrounded by two burning shells, one fusing hydrogen and one fusing helium, and these shells don't burn steadily. They pulse. The helium shell in particular undergoes periodic ignitions called thermal pulses. Every few tens of thousands of years, the helium shell ignites in a brief but intense burst of fusion, dumping a surge of energy into the layers above it. This energy pulse causes the outer layers of the star to expand and contract, each pulse dredging up material from deeper in the star and pushing it toward the surface. With each pulse, the star loses a little more of its outer envelope. The thermal pulses grow stronger as the star ages. The outer layers become increasingly loosely bound. Eventually, the pulsations become so violent that they trigger what astronomers call a superwind, a dramatically enhanced outflow of material from the star's surface. During the superwind phase, the star can lose mass at a rate billions of times greater than the solar wind our sun currently produces. Material streams away from the star at speeds of 10 to 30 kilometers per second, carrying away the bulk of the remaining hydrogen and helium envelope over a period of perhaps only a few tens of thousands of years. This is fast by astronomical standards. The star is essentially undressing itself, shedding its outer layers in a final convulsive effort, leaving the hot, dense core exposed underneath. The process is driven not by a single explosion, but by the cumulative effect of pulsations, radiation pressure, and the simple fact that the outer layers are no longer gravitationally bound tightly enough to resist being pushed away. By the time the superwind subsides, most of the star's original mass has been returned to interstellar space. A star that began its life with perhaps one or two solar masses might retain only half a solar mass or less in its core. The rest is gone, drifting outward, forming the expanding shell of gas that we observe as a planetary nebula. The planetary nebula is stunning. Some of the most beautiful images captured by the Hubble Space Telescope show these structures. Rings and shells and complex shapes of glowing gas lit up by the ultraviolet radiation from the exposed core at the center. The Cat's Eye Nebula, the Ring Nebula, the Helix Nebula. All of these are the cast-off outer layers of dead stars, expanding slowly into interstellar space. But the real story isn't the nebula. The real story is what's left behind after the outer layers have been expelled. What remains at the center is the exposed core, a small, incredibly dense object composed primarily of carbon and oxygen, no longer wrapped in a massive envelope of gas, no longer undergoing any nuclear fusion, just sitting there, white hot from residual heat, radiating energy into space. This is a white dwarf, and now we need to actually understand what this thing is, physically. Because a white dwarf is unlike anything you encounter in everyday life. It's unlike anything on Earth. It's unlike anything in the solar system. The physical conditions inside a white dwarf are so extreme that the matter inside it exists in a state that has no parallel in ordinary human experience. Let's start with the size. A typical white dwarf has a mass of roughly half to about 8/10 the mass of the Sun. That's a tremendous amount of matter. Remember, the Sun is 330,000 times the mass of Earth. A white dwarf containing half the Sun's mass still contains about 165,000 Earth masses. Now here's what's astonishing. All of that mass is compressed into an object roughly the size of Earth. Think about that. An object with 165,000 times the mass of our planet. squeezed into a sphere that's approximately the same diameter as Earth. Earth has a diameter of about 7,900 miles. A typical white dwarf has a similar diameter, but it contains hundreds of thousands of times more mass packed into that same volume. The density that results from this compression is almost beyond comprehension. On Earth, the densest naturally occurring material most people are familiar with is probably gold or lead. Gold has a density of about 19 grams per cubic centimeter. Lead is about 11 grams per cubic centimeter. Water, for comparison, has a density of 1 gram per cubic centimeter. A white dwarf has an average density of roughly 1 million grams per cubic centimeter. Let me say that again. 1 million grams per cubic centimeter. That's about 1 metric ton per cubic centimeter. A piece of white dwarf material the size of a sugar cube would weigh roughly 1 ton. If you could somehow bring a teaspoon of white dwarf material to Earth, it would weigh about 5.5 tons. That's heavier than most elephants. A single teaspoon. You could not lift it. You could not move it. It would crash through any table you placed it on, through any floor, through the foundation of any building. It would sink through the ground like a bullet through paper. This is how dense the matter inside a white dwarf is. Now, how is this possible? How can matter be compressed to such extreme densities? To understand this, you need to think about what matter actually is at the atomic level, and what happens to atoms when you crush them with enough force. Ordinary matter, the stuff you interact with every day, is made of atoms. An atom consists of a nucleus, a tiny dense core containing protons and neutrons, surrounded by a cloud of electrons. The nucleus is incredibly small compared to the atom as a whole. If an atom were the size of a football stadium, the nucleus would be about the size of a marble sitting at the center of the field. Everything else, the vast majority of the atom's volume, is occupied by the electron cloud. But here's the thing. That electron cloud is mostly empty space. Atoms are almost entirely empty. The reason solid objects feel solid, the reason you can't push your hand through a table, is not because atoms are tightly packed balls of matter. It's because the electron clouds of neighboring atoms repel each other through electromagnetic forces. The solidity you feel is an electromagnetic illusion. The atoms themselves are mostly nothing. In the core of a dying star, as gravity compresses the matter more and more, something happens to these atoms. The pressure becomes so enormous that the electron clouds can no longer maintain their structure. The atoms are crushed, not just pushed closer together. They are fundamentally destroyed as atoms. The electrons are stripped away from their nuclei. Every atom in the core loses its electrons. What you're left with is not atoms anymore. It's a soup of bare nuclei, carbon nuclei and oxygen nuclei, swimming in a dense sea of free electrons. This is called a plasma, but it's a very different kind of plasma than what you'd find in, say, a neon sign or on the surface of the sun. This plasma is extraordinarily dense. The nuclei and electrons are packed together far more tightly than atoms ever are in ordinary matter. In normal matter, atoms are separated by distances that are large compared to the size of the nuclei. In a white dwarf, the particles are compressed into a volume that's a tiny fraction of what ordinary atoms would occupy. The empty space that existed within the atoms has been squeezed out. The matter has been compressed far beyond what atoms normally allow. This is why a white dwarf is so dense. It's not made of atoms in any meaningful sense. It's made of a crushed electron nuclear plasma, where the particles are packed together with almost none of the empty space that gives ordinary matter its volume. All the fluffiness of atoms, all that empty space between the nucleus and the electron cloud, has been eliminated by gravitational compression. And now we arrive at the central mystery. This white dwarf is sitting there in space. It has enormous mass compressed into a tiny volume. Gravity is pulling all that mass inward with tremendous force. And there's no fusion happening in the core, no nuclear reactions generating heat, no energy source pushing back against gravity. In a normal star, fusion provides the thermal pressure that holds the star up. But a white dwarf has no fusion. The fuel is exhausted. The carbon and oxygen just sit there. They will never fuse, not in a star of this mass. So what's holding it up? What prevents this incredibly dense object from collapsing further? If you took a ball of matter with half the mass of the sun and turned off all the energy sources, you'd expect gravity to crush it down further and further, until it became something even smaller and denser. You'd expect it to keep collapsing. But it doesn't. The white dwarf just sits there. Stable, not collapsing, not expanding, not doing anything except slowly radiating away its stored heat. Something is providing an outward pressure that balances gravity. But that pressure has nothing to do with heat or temperature. It has nothing to do with nuclear fusion or any kind of energy generation. The pressure that supports a white dwarf against gravitational collapse comes from somewhere entirely different. It comes from quantum mechanics, from one of the most fundamental and strange rules governing the subatomic world. And this pressure is so powerful, so absolute, that it can hold up the mass of half a sun without any fuel, without any energy source, potentially forever. The white dwarf is not alive in any stellar sense. It generates no energy. It creates no new elements. It has no engine, no furnace, no mechanism for sustaining itself. And yet, it does not collapse. It persists, stable and enduring across timescales that make the age of human civilization look like the blink of an eye. This object will outlast virtually everything else in the cosmos. Long after the last stars have burned out, long after the galaxies have scattered and faded, white dwarfs will still be there, slowly cooling, slowly dimming, but never collapsing. The reason for this extraordinary stability is rooted not in any force we can see or feel in our daily lives, but in a quantum mechanical principle that governs how electrons behave when they're forced into extreme confinement. It's a rule that says there's a limit to how much you can compress certain types of particles, a floor beyond which matter simply refuses to be pushed further. And this quantum floor is what keeps every white dwarf in the universe from imploding under its own gravity. To understand the white dwarf is to understand something profound about the nature of matter itself. Because what you're looking at when you look at a white dwarf is not just a dead star. It's a demonstration of what happens when the familiar rules of everyday physics give way to the deeper rules of quantum mechanics. The matter inside a white dwarf has been pushed past the point where ordinary physics can describe it. The atoms have been destroyed. The normal forces that give matter its structure have been overwhelmed. And in their place, something deeper has taken over. Something that has nothing to do with heat or energy or motion in the classical sense. Something that is built into the very fabric of how particles exist. Every white dwarf in the universe is a monument to this quantum reality. There are estimated to be billions of white dwarfs in the Milky Way alone, perhaps as many as 10 billion. They represent the final state of the vast majority of stars that have ever existed. About 97% of all the stars in the Milky Way will eventually become white dwarfs. The Sun will become one. Most of the stars you see in the night sky will become one. They are the most common endpoint of stellar evolution. They are everywhere. And every single one of them is being held up not by fire, not by energy, not by any process that generates power, but by a quantum mechanical rule about how electrons behave. These remnants are the embers of the galaxy, tiny, dense, slowly fading points of light scattered throughout the Milky Way. Some are incredibly hot, with surface temperatures exceeding 180,000 degrees Fahrenheit, fresh from their birth as newly exposed stellar cores. Others have been cooling for billions of years, their surfaces dimming toward temperatures lower than the sun's. But whether hot or cool, whether bright or faint, every single one of them is supported by the same mechanism, the same quantum pressure, the same fundamental refusal of electrons to be compressed beyond a certain point. And what makes this even more remarkable is that this supporting pressure asks for nothing in return. Fusion requires fuel. Thermal pressure requires heat. Both of these are temporary. They last only as long as the fuel or heat lasts. But the quantum pressure inside a white dwarf requires no fuel, no heat, no input of any kind. It simply exists as a consequence of how electrons are. As long as the electrons are there, the pressure is there. It doesn't diminish over time, it doesn't weaken, it doesn't run out. The white dwarf could sit there for 1 trillion years, and the pressure holding it up would be exactly the same as it was the day the star died. This is why a white dwarf can survive for so long. It has an eternal support mechanism. No fuel to run out, no fire to extinguish, just a quantum rule operating continuously, holding the remnant in its compressed state against the relentless inward pull of gravity. It is a kind of immortality, at least structurally. The white dwarf will cool. It will dim. It will eventually radiate away all of its stored thermal energy, but it will never collapse. Not from cooling, not from age, not from running out of anything. The support is built into the fabric of matter itself. What we're about to explore is the nature of that support, the quantum mechanical principle that makes all of this possible. Because understanding that principle is the key to understanding everything about what happens inside a white dwarf. The matter, the density, the stability, the structure, the longevity. All of it traces back to one rule about how electrons behave when they're packed together under extreme conditions. And that rule is stranger and more profound than most people realize. So what is this mysterious force? What is this quantum pressure that holds up a dead star without any fuel, without any heat source, without any engine of any kind? To answer that, we need to leave the world of astronomy for a moment and enter the world of quantum mechanics. Because the force that supports a white dwarf doesn't come from anything you can see or touch or feel in your everyday life. It comes from a rule about how subatomic particles behave. A rule that was discovered in the 1920s by a physicist named Wolfgang Pauli. And this rule, known as the Pauli exclusion principle, is one of the most important discoveries in the history of physics. It governs how atoms work, how chemistry works, how the periodic table is structured, and as it turns out, how dead stars survive. To understand the Pauli exclusion principle, you first need to understand something about particles. In quantum mechanics, every particle has a set of properties that describe its state. Think of these properties as a kind of address. Just as every house has a unique address consisting of a street number, a street name, a city, and a zip code, every particle in a quantum system has a unique set of quantum numbers that describe where it is, how fast it's moving, and how it's spinning. These quantum numbers define what physicists call a quantum state. Now, here's where the Pauli exclusion principle comes in. It says that no two electrons can occupy the same quantum state at the same time in the same system. That's it. That's the rule. It sounds simple, almost trivially simple, but its consequences are enormous. Two electrons can't have the same quantum address. If one electron is already in a particular state, with a particular set of quantum numbers describing its energy, its position, and its spin, then no other electron can be in that exact same state. The second electron has to find a different state, a different address. This isn't a suggestion, it's not a tendency. It's an absolute law of nature. Electrons simply cannot violate it. There is no force in the universe strong enough to make two electrons occupy the same quantum state. It's not that they resist being pushed into the same state. It's that doing so is physically impossible. The universe does not allow it. Period. In ordinary matter, this principle is what gives atoms their structure. Consider a carbon atom, which has 6 electrons. You might wonder why all 6 electrons don't just fall down to the lowest energy state closest to the nucleus. After all, that's the state with the least energy, and systems in nature tend to seek the lowest energy configuration. But they can't all fall to the lowest state because the Pauli exclusion principle forbids it. Only 2 electrons can occupy the lowest energy level, and they can only do so because they have opposite spins. Spin is one of the quantum numbers that defines a particle's state. Each energy level can hold 2 electrons, one spinning up and one spinning down. After that, the level is full. No more electrons are allowed. The remaining electrons have to occupy higher energy levels. This is why atoms have electron shells. This is why the periodic table has its structure. This is why chemistry works the way it does. The Pauli exclusion principle forces electrons into progressively higher energy states as lower states fill up. Without this principle, all electrons would collapse to the lowest energy level, atoms would have no structure, and chemistry as we know it would not exist. There would be no molecules, no compounds, no water, no DNA, no life. The Pauli exclusion principle is arguably one of the most important rules in the universe for making complex matter possible. Now, let's take this principle and apply it to the interior of a white dwarf. Remember what we established. A white dwarf is a stellar remnant with roughly half the mass of the Sun, compressed into a volume about the size of Earth. The atoms have been destroyed. The electrons have been stripped from their nuclei. What you have is a dense plasma of bare carbon and oxygen nuclei swimming in a sea of free electrons. These electrons are not bound to any particular nucleus. They're free to move throughout the interior. But they're confined to the volume of the white dwarf by gravity. They can't escape because the gravitational pull of all that mass holds them in. So you have an enormous number of electrons, roughly 10 to the power of 57 electrons, crammed into a relatively small volume. And this is where the Pauli exclusion principle becomes critically important. As the electrons are compressed into a smaller and smaller volume, the available quantum states begin to fill up. Think of it like seats in a theatre. When the theatre is mostly empty, everyone can sit wherever they want. There are plenty of available seats. But as more and more people enter and the theatre fills up, the remaining seats become scarce. Eventually the lower sections fill up first because they're closest to the stage, and latecomers are forced to sit in higher and higher sections. The same thing happens with electrons in a white dwarf. As gravity compresses the matter, squeezing the electrons into a smaller volume, the low-energy quantum states fill up quickly. The first electrons settle into the lowest available states. But those states can only hold so many electrons. Once a state is full, no more electrons can enter it. The next electrons have to occupy higher energy states. As compression continues, more and more of the low energy states become occupied. Electrons are forced into progressively higher and higher energy levels. And here's the key insight. Electrons in higher energy states move faster. They have more momentum, and particles with more momentum exert more pressure on their surroundings. As gravity compresses the white dwarf, it forces electrons into higher energy states, which means the electrons are moving faster, which means they're pushing back harder against the walls of their confinement. This pushback, this outward pressure generated by electrons being forced into higher and higher energy states, because the lower states are already full, is electron degeneracy pressure. It's not thermal pressure. It has nothing to do with temperature. In a normal star, particles move fast because the gas is hot. The hotter the gas, the faster the particles move, the more pressure they exert. If the gas cools down, the particles slow down and the pressure drops. That's thermal pressure. It depends entirely on temperature. Degeneracy pressure is fundamentally different. The electrons in a white dwarf are moving fast, not because the interior is hot, but because the Pauli exclusion principle forces them into high energy states. Even if you could somehow cool the white dwarf to absolute zero, even if you removed every last bit of thermal energy from the system, the electrons would still be moving fast. They would still be in those high energy states, because there's nowhere else for them to go. The lower states are full. The electrons can't drop down to lower energy levels, because those levels are already occupied by other electrons. The Pauli exclusion principle forbids it. So the electrons are stuck in their high energy states, moving rapidly, exerting pressure, regardless of the temperature. This is a staggering concept when you really think about it. In our everyday experience, pressure and temperature are intimately linked. Hot things expand because the particles inside them are moving faster and pushing outward. Cold things contract because the particles are moving more slowly. This is so intuitive that we rarely question it. But in a white dwarf, this connection between temperature and pressure is broken. The pressure exists independently of the temperature. You could cool a white dwarf for 1 billion years, draining away its thermal energy bit by bit, and the degeneracy pressure holding it up would not change at all. Not one bit. The support is permanent. It doesn't depend on the white dwarf staying hot. It doesn't depend on any energy source. It depends only on the fact that electrons obey the Pauli exclusion principle. And since the Pauli exclusion principle is a fundamental law of quantum mechanics, not something that can wear out or be used up, the pressure is effectively eternal. Let me try to make this even clearer with a thought experiment. Imagine you have a box full of tennis balls. The box is divided into shelves, and each shelf can hold exactly 2 tennis balls. You start filling the box from the bottom shelf. You place 2 tennis balls on the lowest shelf, then 2 on the next shelf up, then 2 on the next. As the box fills up, the tennis balls on the higher shelves are higher up and have more gravitational potential energy. Now imagine someone pushing down on the top of the box, trying to compress it, trying to make it smaller. What happens? The tennis balls on the upper shelves resist being pushed down because the shelves below them are already full. There's no room to move down. The balls on this lower shelves can't accommodate any newcomers, so the whole system resists compression. This resistance has nothing to do with temperature, it has nothing to do with the tennis balls being hot or energetic. It's purely a consequence of the fact that each shelf has a maximum capacity. The quantum states in a white dwarf work the same way. Each state has a maximum capacity of 1 electron with a given set of quantum numbers. When all the low energy states are full, the electrons in the high energy states can't move down. They're stuck. And their presence in those high energy states generates pressure that resists further compression. This is the quantum flaw I mentioned a moment ago. There's a limit to how much you can compress this matter. Not because of any force in the traditional sense, but because the rules of quantum mechanics simply don't allow the electrons to be packed any tighter. The electrons have run out of available lower energy states. They have nowhere to go. And their refusal to be compressed further, their quantum mechanical stubbornness, is what holds up the entire white dwarf against the crushing force of gravity. Now, I want to draw a very clear distinction here because this is where most explanations get muddled. People sometimes describe electron degeneracy pressure as a force, like gravity or electromagnetism. But it's not exactly a force in the traditional sense, it's more like a constraint. Gravity is actively pulling the matter inward. But degeneracy pressure isn't actively pushing the matter outward the way a spring pushes back when you compress it. Instead, it's more like a wall. It sets a limit. It says the matter cannot be compressed beyond a certain point because doing so would require electrons to violate the Pauli exclusion principle. And since that's impossible, the compression simply stops. The matter reaches a state of equilibrium where the gravitational force trying to compress it further is balanced by the quantum mechanical impossibility of compressing it anymore. This equilibrium is extraordinarily stable. In a normal star, the balance between gravity and thermal pressure is dynamic. If the star produces a little more energy than usual, it expands slightly. If it produces a little less, it contracts slightly. The star is constantly adjusting, constantly seeking balance, and if you remove the energy source entirely, the balance collapses and the star contracts. But a white dwarf's equilibrium is not dynamic in this way. It's static. The degeneracy pressure doesn't fluctuate. It doesn't depend on any ongoing process. It's just there, set by the density of the matter and the laws of quantum mechanics. As long as the mass doesn't change, the equilibrium doesn't change. The white dwarf just sits there in perfect balance, not because anything is actively maintaining the balance, but because the balance is built into the physics of the matter itself. This also explains something else that's deeply counterintuitive about white dwarfs. In a normal star, more massive stars are larger. The sun is bigger than a red dwarf. A blue giant is bigger than the sun. More mass means more gravity, but also more fuel, more fusion, more thermal pressure, and a larger star. The relationship between mass and size is straightforward. More mass, bigger star. White dwarfs are the opposite. More massive white dwarfs are actually smaller. This sounds completely backwards, but it follows directly from how degeneracy pressure works. When you add mass to a white dwarf, you increase the gravitational force trying to compress it. The electrons respond by being squeezed into even higher energy states, which increases the degeneracy pressure. But the increased pressure doesn't cause the white dwarf to expand. Instead, the matter reaches a new equilibrium at a smaller radius. The white dwarf gets denser and more compact. A white dwarf with the mass of the Sun is actually smaller in radius than a white dwarf with half the mass of the Sun. This inverse relationship between mass and size is one of the signature features of objects supported by degeneracy pressure. It's completely alien to our everyday intuition, but it follows inevitably from the quantum mechanics of confined electrons. And this inverse relationship leads us to something extraordinary, to a limit. Because if adding mass makes a white dwarf smaller and denser, what happens if you keep adding mass? The white dwarf gets smaller and smaller. The electrons are squeezed into higher and higher energy states. They move faster and faster. And here's the thing. There's a speed limit in the universe. Nothing can move faster than the speed of light, not even electrons. As the electrons in a white dwarf are forced into increasingly high energy states by the increasing gravitational compression, they approach speeds closer and closer to the speed of light. They become relativistic. And when electrons become relativistic, the nature of the degeneracy pressure changes. At ordinary speeds, doubling the compression roughly doubles the degeneracy pressure. The pressure increases fast enough to keep up with the increasing gravity from the added mass. But at relativistic speeds, this relationship breaks down. The pressure still increases with compression, but it increases more slowly. It can no longer keep pace with the increasing gravity. This means there is a maximum mass that electron degeneracy pressure can support. If you keep adding mass to a white dwarf, eventually the electrons would need to move faster than the speed of light to provide enough pressure to hold it up. And since nothing can exceed the speed of light, this is impossible. The pressure maxes out. Gravity wins. This maximum mass is called the Chandrasekhar limit, named after the brilliant Indian-American astrophysicist Subrahmanyan Chandrasekhar, who calculated it in 1930. He was only 19 years old at the time. He was travelling by steamship from India to England to begin his graduate studies at Cambridge, and during the voyage, he worked through the mathematics of how electrons behave in extremely dense matter when their speeds approach the speed of light. His calculation showed that there is a definite upper mass limit for white dwarfs. The exact value he derived was approximately 1.4 times the mass of the Sun. Any white dwarf below this mass can be supported indefinitely by electron degeneracy pressure. The electrons have enough quantum room to provide the pressure needed to balance gravity. But a white dwarf at or above this mass cannot be supported. The electrons simply cannot move fast enough to generate sufficient pressure. The degeneracy support fails. This was a revolutionary finding. It was also controversial at the time. The famous astrophysicist Arthur Eddington publicly ridiculed Chandrasekhar's result, finding the implication absurd. The implication being that if a star were too massive, nothing could stop its collapse. The idea that nature would allow a star to keep collapsing without limit was deeply unsettling to many physicists. But Chandrasekhar was right. The mathematics was rigorous, and over the following decades, observation after observation confirmed the limit. No white dwarf has ever been observed with a mass significantly above 1.4 solar masses. They don't exist. They can't exist. The physics simply won't allow it. The Chandrasekhar limit is one of the most important numbers in astrophysics. It draws a hard line in the universe. Below this mass, stellar remnants can be supported by electron degeneracy pressure and exist as stable white dwarfs. At or above this mass, electron degeneracy pressure fails, and something far more dramatic must happen. The matter must collapse further, to densities that dwarf even the extreme densities of a white dwarf. into objects where electrons and protons are crushed together into neutrons, into objects where the physics changes completely. But that is a story of its own. For now, what matters is understanding what the Chandrasekhar limit means for white dwarfs. It means there is a ceiling, a maximum weight that the quantum floor can bear. Below that ceiling, the white dwarf is stable, perfectly, permanently stable. The electrons faithfully obey the Pauli exclusion principle, maintaining their positions in their high-energy quantum states, providing an unwavering outward pressure that balances gravity exactly. The white dwarf doesn't need fuel. It doesn't need an energy source. It doesn't need anything. It just exists in this balanced state, supported by the fundamental rules of quantum mechanics, enduring for timescales that stretch beyond anything we can easily comprehend. Think about what this means for the life story of a star. A star like the Sun spends billions of years burning fuel, hydrogen first, then helium. It generates enormous amounts of energy. It lights up its corner of the galaxy. It makes life possible on planets orbiting around it. And then, when the fuel runs out, when the fusion stops, when the fire goes out, the star doesn't disappear. It doesn't collapse into nothing. It transforms into something new, something strange and dense and unfamiliar. It becomes a white dwarf. And in this new form, supported not by fire but by a quantum law, it endures. Not for billions of years, for trillions. The thermal pressure that held the star up during its active life was temporary. It lasted only as long as the fuel lasted. But the degeneracy pressure that holds up the white dwarf is not temporary. It is, for all practical purposes, permanent. The fuel-burning phase of a star's life is actually the brief part. The white dwarf phase is the long part, overwhelmingly, incomparably long. The Sun, for example, will spend about 10 billion years on the main sequence, burning hydrogen. Then, perhaps a billion more years or so going through its red giant and helium-burning phases. Call it roughly 11 billion years total of active life. But once it becomes a white dwarf, it will persist for trillions of years. Tens of trillions. Hundreds of trillions. Perhaps longer. The white dwarf phase isn't the epilogue. It's the main story. The fusion-burning phase is just the introduction. The white dwarf is what the star spends most of its existence as. And during all that time, the degeneracy pressure never wavers, never weakens, never needs to be renewed or refreshed. It simply is. A consequence of the laws of physics that will continue to operate as long as those laws hold. There is something deeply beautiful about this. A star burns gloriously for billions of years, flooding space with light and heat. And then, when the burning stops, instead of vanishing, it enters a new kind of existence. A quiet existence. A stable existence. Held together not by violence and fire, but by one of the quietest, most subtle rules in physics. The rule that says electrons cannot share the same quantum state. That's all it is. That's all that stands between a white dwarf and gravitational collapse. A simple quantum mechanical rule about how particles are allowed to be arranged. And this rule operates silently, invisibly, without any fanfare, inside every white dwarf in the universe. Inside the billions of white dwarfs scattered throughout the Milky Way. Inside the trillions more scattered throughout other galaxies. Every single one of them is a demonstration of the Pauli exclusion principle in action on a cosmic scale. Every single one of them is being held up by the same force, the same quantum stubbornness of electrons refusing to share their states. It's the same principle that gives structure to the atoms in your body, that determines the shape of the periodic table, that makes chemistry and biology possible. Except in a white dwarf, it's operating under conditions so extreme that it becomes the dominant force in the entire object. In your body, the Pauli exclusion principle shapes atoms. In a white dwarf, it holds up a star. What we've uncovered here is something profound. The quantum world, The world of subatomic particles and probabilistic behavior and uncertainty principles is often treated as abstract, something that matters only in laboratories or in equations on a chalkboard. But the white dwarf shows us that quantum mechanics operates on the largest scales. It holds up objects the mass of stars. It determines the fate of stellar remnants that will outlast nearly everything else in the universe. The quantum world is not just an abstract theory, it's the architecture of the cosmos, and nowhere is that more dramatically demonstrated than inside a white dwarf, where a simple rule about electrons is single-handedly preventing the gravitational collapse of a star's corpse. The white dwarf is not just an astronomical object, it's a quantum mechanical object. Its very existence depends on the laws of the subatomic world operating at a cosmic scale. And understanding that connection, seeing how the physics of the incredibly small governs the behavior of the incredibly large, is one of the most profound realizations in all of science. So we know what holds a white dwarf up: electron degeneracy pressure, a quantum mechanical phenomenon that has nothing to do with heat or fusion, or any energy source. It's a permanent support built into the fabric of matter itself. But knowing what holds the object up is only part of the picture. The next question is equally fascinating and far less often discussed. What is actually in there? If you could somehow slice a white dwarf in half and look inside, what would you see? What is the interior made of? What state is the matter in? Is it solid? Is it liquid? Is it something else entirely? Because the answer turns out to be stranger and more remarkable than almost anyone expects. The inside of a white dwarf is not uniform. It's not just a featureless ball of compressed stuff. It has structure, it has layers, and the matter at its core exists in a physical state that has no equivalent anywhere on Earth. A state where the rules of solid and liquid blur together into something entirely new. Let's start with composition. What elements make up the interior of a typical white dwarf? The answer depends on the star that produced it, but for the most common white dwarfs, the ones formed from stars roughly similar to our Sun, the interior is composed primarily of carbon and oxygen. These two elements are the final ash products of the nuclear fusion that occurred during the star's active life. Remember, the star spent most of its life fusing hydrogen into helium in its core. Then, in its later stages, it fused helium into carbon through the triple alpha process. During that same phase, some of the carbon captured additional helium nuclei to produce oxygen. When the star could no longer sustain fusion, these elements remained in the core as the permanent residue of the star's nuclear burning. They are the ashes of a fire that has gone out: carbon and oxygen, two elements you're intimately familiar with. Carbon is what diamonds are made of. It's what graphite in your pencil is made of. It's the backbone of every organic molecule in your body. Oxygen is what you breathe. Together, they make up carbon dioxide, the gas you exhale. These are common, everyday elements on Earth, but inside a white dwarf, they exist under conditions so extreme that they bear no resemblance whatsoever to the carbon and oxygen you encounter in daily life. The carbon in a diamond is arranged in a crystal lattice where each carbon atom is bonded to 4 neighbors. It's hard because those bonds are strong, but inside a white dwarf, there are no chemical bonds. The atoms have been completely ionized. Every electron has been stripped away. What remains are bare carbon nuclei, each containing 6 protons and 6 neutrons, and bare oxygen nuclei, each containing 8 protons and 8 neutrons. These nuclei are positively charged because they've lost all their electrons. The electrons, meanwhile, form a separate sea of negatively charged particles, filling the entire interior. The nuclei and the electrons coexist in the same space, but they're behaving very differently from each other. The electrons are degenerate. They're the ones providing the pressure that holds the white dwarf up. They're in their quantum mechanical high-energy states, zipping around at enormous speeds, obeying the Pauli exclusion principle. The nuclei, on the other hand, are much heavier than the electrons. A carbon nucleus is about 22,000 times more massive than an electron. An oxygen nucleus is about 29,000 times more massive. Because of their much greater mass, the nuclei are not degenerate under the conditions found in a white dwarf. They behave more classically, They respond to temperature. They can gain or lose thermal energy. And crucially, they interact with each other through their positive electric charges. Now, let's talk about the structure of a white dwarf, because the interior is not a single homogeneous mass. It has distinct layers, each with different physical properties, and understanding these layers helps paint a picture of what this object truly looks like on the inside. The outermost layer of a white dwarf is an incredibly thin atmosphere. When I say thin, I mean astonishingly thin relative to the size of the object. The atmosphere of a white dwarf might be only a few hundred meters thick. On an object with a radius of several thousand kilometers, that's practically nothing. It's like a coat of paint on a bowling ball. But this thin atmosphere is important because it's what we actually observe when we look at a white dwarf with a telescope. The light we see comes from this atmospheric layer. The composition of the atmosphere tells us a lot about the white dwarf's history and classification. Most white dwarfs have atmospheres composed primarily of hydrogen. These are classified as Da white dwarfs, and they make up roughly 80% of all known white dwarfs. The hydrogen floats to the surface because it's the lightest element. Even though the star shed most of its hydrogen during its red giant phase, a tiny residual amount remains. And in the intense gravitational field of a white dwarf, where the surface gravity is roughly 100,000 to 300,000 times stronger than Earth's surface gravity, the elements separate by weight extremely efficiently. Hydrogen, being the lightest, rises to the top. Helium sinks below it. The heavier elements sink even deeper. This gravitational settling happens relatively quickly in astronomical terms, over timescales of perhaps thousands to millions of years. The result is a beautifully stratified structure where the elements are sorted by atomic weight with remarkable precision. Below the hydrogen atmosphere, there is typically a thin layer of helium. This layer is also very thin compared to the total radius of the white dwarf, but it's thicker than the hydrogen atmosphere above it. The helium layer might extend for several kilometers or tens of kilometers. Together, the hydrogen and helium layers form what astronomers call the envelope of the white dwarf. The envelope is non-degenerate, meaning the matter in these layers behaves more or less like ordinary hot gas. The densities in the envelope are high by Earth standards, but nowhere near the densities found deeper inside. The envelope is where heat from the interior slowly diffuses outward before being radiated into space from the surface. It acts like a blanket, controlling the rate at which the white dwarf cools. The thickness and composition of the envelope have a significant effect on how quickly the white dwarf loses its heat. A thicker hydrogen envelope insulates the interior more effectively, slowing the cooling process. This is why the details of the envelope matter for astronomers trying to determine the ages of white dwarfs based on their temperatures. Not all white dwarfs have hydrogen atmospheres, though. About 20% of white dwarfs have atmospheres dominated by helium instead. These fall into several spectral subtypes, depending on what features appear in their light. The most prominent are the DB white dwarfs, which show clear helium absorption lines in their spectra. In these objects, the hydrogen layer is either missing entirely or so thin as to be undetectable. How a white dwarf ends up without hydrogen on its surface is still an active area of research. It might be the result of the star losing its hydrogen more completely during the red giant phase. It might be related to interactions with a companion star in a binary system, or it might involve processes in the white dwarf itself that mix or burn away the surface hydrogen. There are even rarer types. Some white dwarfs show carbon in their atmospheres. Some show metals, which in astronomical terminology means any element heavier than helium. The presence of metals in a white dwarf atmosphere is puzzling, because gravitational settling should quickly drag those heavy elements below the surface. If we see metals in a white dwarf's atmosphere, it usually means something is actively replenishing them. The most common explanation is that the white dwarf is accreting material from its environment, perhaps from asteroids, comets, or the debris of a disrupted planetary system that once orbited the star. This is actually one of the most exciting areas of white dwarf research. By studying the metals in white dwarf atmospheres, astronomers can determine the chemical composition of the rocky material falling onto the star. This effectively allows them to analyze the composition of exoplanetary material, the remnants of worlds that once existed around these dead stars. It's a forensic analysis of destroyed planets conducted by studying the surface of their parent star's corpse, and the forensic results have been extraordinary. Astronomers have now studied the polluted atmospheres of hundreds of white dwarfs, and what they found paints a vivid picture of the rocky material falling onto these dead stars. The chemical signatures reveal the presence of elements like silicon, magnesium, iron, calcium, and aluminum in proportions that closely match the bulk composition of rocky bodies in our own solar system. In some cases, the ratios of these elements suggest the infalling material came from differentiated bodies, objects large enough that their interiors had separated into distinct layers with an iron-rich core, a silicate-rich mantle, and a lighter crust, much like Earth. This means the white dwarfs are consuming the shattered remains of objects that were once geologically complex worlds, bodies with internal structure, with cores and mantles, objects that might once have been similar to the rocky planets in our own solar system. Even more remarkably, some polluted white dwarfs show evidence of water. Not water in the familiar liquid form, but the chemical signature of oxygen in excess of what can be explained by rock-forming minerals alone. The most straightforward explanation for this excess oxygen is that the accreted material contained significant amounts of water, either as ice or locked into hydrated minerals. This suggests that water-rich asteroids, similar to certain classes of meteorites found on Earth, are being consumed by these white dwarfs. In at least one case, a white dwarf designated GD61, the evidence strongly implies that the infalling material came from a body that contained roughly 26% water by mass. That's an object that was essentially a water world in miniature, an asteroid rich in ice, now being devoured by a dead star. These observations represent one of the few ways we can directly measure the chemical composition of rocky material around other stars. We can't easily analyze the surfaces of distant exoplanets, but when those planets or their asteroids are destroyed and fall onto a white dwarf, the white dwarf's atmosphere becomes a chemical record of what those bodies were made of. Every polluted white dwarf is a gravestone inscribed with the chemical epitaph of worlds that no longer exist. But the atmosphere and the envelope are just the skin. They represent a tiny fraction of the white dwarf's total mass. The overwhelming majority of the white dwarf, more than 99% of its mass, is in the core. And the core is where things get truly exotic. The core of a typical carbon-oxygen white dwarf is an environment unlike anything else in the universe except other white dwarfs. The density here is staggering, on the order of 1 million grams per cubic centimeter or more. The pressure is immense, and the matter exists in a state that challenges our usual categories of solid, liquid, and gas. Let me describe what's happening in the core in more detail. You have bare carbon and oxygen nuclei stripped of all their electrons, packed tightly together. These nuclei carry positive electric charges, so they repel each other electromagnetically. At the same time, they're confined in a small volume by the immense gravity, and they're immersed in a sea of degenerate electrons that fills the spaces between them. The degenerate electron sea actually plays an important role here, beyond just providing pressure. The electrons are so dense and so uniformly distributed that they effectively screen the electric charges of the nuclei. Each nucleus is surrounded by a cloud of electrons that partially cancels its positive charge. This screening reduces the repulsive force between neighboring nuclei, allowing them to exist closer together than they otherwise could. Now, here's where it gets fascinating. When a white dwarf first forms, it's extremely hot. The core temperature can be hundreds of millions of degrees. At these temperatures, the nuclei have a lot of thermal energy. They vibrate and jostle around within the sea of electrons. The core at this stage behaves somewhat like a very dense liquid. The nuclei are free to move around relative to each other. There's no fixed structure, it's fluid, chaotic, with nuclei bouncing off each other and moving through the electron sea more or less freely. But the white dwarf is cooling. Slowly, relentlessly, it's radiating away its thermal energy into space. The surface glows, and that glow carries energy away from the interior. Over millions and then billions of years, the core temperature drops. And as the temperature drops, something remarkable happens. The nuclei slow down, they lose thermal energy. Their vibrations become less vigorous, and at some point when the core temperature drops below a critical threshold, the nuclei begin to lock into fixed positions relative to each other. They stop moving freely and arrange themselves into a regular, repeating pattern. A lattice. A crystal lattice. The core of the white dwarf begins to crystallize. Think about that for a moment. The interior of a dead star, an object with half the mass of the sun compressed into a volume the size of Earth, is literally forming a crystal. The carbon and oxygen nuclei are arranging themselves into an orderly structure, much like atoms arrange themselves in a crystal of salt or ice when a liquid freezes. Except this crystal is made not of atoms, but of bare atomic nuclei, packed at densities millions of times greater than any crystal on Earth, and it's forming inside a stellar corpse that's slowly cooling over cosmic timescales. The crystallization process doesn't happen all at once. It begins at the center of the white dwarf, where the density is highest, and the conditions for crystallization are reached first. From there, the crystal front grows outward over time as the white dwarf continues to cool. The core gradually solidifies from the inside out, forming an ever-growing crystalline heart surrounded by a still, liquid outer core. Eventually, most of the core will have crystallized. The crystal structure that forms is thought to be a body-centered cubic lattice. This is one of the standard arrangements in crystallography, a structure where each nucleus sits at the center of a cube, defined by 8 neighboring nuclei. The spacing between the nuclei is incredibly small by everyday standards, on the order of a few hundredths of an angstrom, far smaller than the spacing between atoms in any ordinary crystal. But relative to the size of the nuclei themselves, the spacing is actually quite large. The nuclei are held in their positions not by chemical bonds, which don't exist in this environment, but by the balance between their mutual electromagnetic repulsion and the confining effect of the electron sea and gravity. It's a lattice made not of bonded atoms, but of charged particles suspended in an equilibrium of forces. This crystallization releases energy. When a liquid freezes, it releases latent heat. The same thing happens in a white dwarf. As the core crystallizes, the formation of the ordered lattice releases gravitational and thermal energy. This energy temporarily slows the cooling of the white dwarf. For a period of time, perhaps 1 billion years or more, a crystallizing white dwarf cools more slowly than it otherwise would, because the crystallization process is adding energy back into the system. This has important consequences for astronomers who use white dwarfs as cosmic clocks. Because white dwarfs cool at predictable rates, and because cooler white dwarfs are older, astronomers can estimate the ages of stellar populations by measuring the temperatures of their white dwarfs. But if crystallization slows the cooling process, then the age estimates need to be adjusted. A crystallizing white dwarf is older than its temperature alone would suggest. This effect was predicted theoretically decades ago and was confirmed observationally by the Gaia spacecraft in 2019. Gaia measured the brightness and colors of hundreds of thousands of nearby white dwarfs, and it found a pileup of white dwarfs at a specific brightness level, a range where there were more white dwarfs than expected. This pileup corresponded exactly to the predicted crystallization temperature. White dwarfs were lingering at that brightness because crystallization was slowing their cooling. It was direct observational evidence that the cores of white dwarfs are turning into crystals. It's worth pausing here to understand why crystallization happens at a specific temperature threshold rather than gradually. The physics comes down to a competition between two effects. The positively charged nuclei repel each other electromagnetically. At high temperatures, the nuclei have enough thermal energy to overcome this repulsion and move freely through the electron sea. They behave like a liquid. But as the temperature drops, the thermal energy of the nuclei decreases. At some point, the electromagnetic repulsion energy between neighboring nuclei becomes much larger than their thermal energy. When this happens, the nuclei can no longer move freely. They become trapped by the repulsive forces of their neighbors, locked into positions of minimum energy. The ratio between the electromagnetic energy and the thermal energy is described by parameter physicists called the Coulomb coupling parameter, usually denoted by the Greek letter gamma. When gamma is low, the thermal energy dominates, and the nuclei behave like a gas or liquid. When gamma exceeds a critical value of roughly 175, the electromagnetic interactions dominate, and the nuclei freeze into a lattice. This transition is sharp. It's not a gradual stiffening. It's a genuine phase transition, similar to water freezing into ice at 0 degrees Celsius. One moment, the nuclei are fluid. Next, they're locked in place. And because the density increases toward the center of the white dwarf, the center reaches the critical gamma value first. The crystallization front then migrates outward as the white dwarf continues to cool, like a pond freezing from the bottom up. The Gaia data confirm this beautifully. When astronomers plotted the luminosities and colors of hundreds of thousands of white dwarfs on what's called a Hertzsprung-Russell diagram, they found a distinct clustering of white dwarfs at a specific luminosity range. There were more white dwarfs at that brightness than the standard cooling models predicted. This pileup matched precisely the luminosity at which core crystallization was expected to begin, releasing latent heat and stalling the cooling process. White dwarfs were spending extra time at that brightness, accumulating in the data like cars slowing down at a toll booth on a highway. The pileup was unmistakable. It was one of the most satisfying confirmations of a theoretical prediction in modern stellar astrophysics. Now, I mentioned earlier that most white dwarfs have carbon-oxygen cores, but not all of them do. The composition of the core depends on the mass of the original star that produced the white dwarf, and different progenitor masses lead to different compositions. At the low end of the mass range, very low-mass white dwarfs can have cores made primarily of helium. These helium white dwarfs form from stars that never got hot enough to ignite helium fusion in their cores. Normally, this would mean extremely low-mass stars, because even modest mass stars eventually reach the temperatures needed for helium fusion. But there's a problem. The lowest mass stars, the red dwarfs, have lifetimes that vastly exceed the current age of the universe. A red dwarf with 1/10 the mass of the Sun will burn hydrogen for trillions of years. It won't become a white dwarf for an incredibly long time, far longer than the 13.8 billion years the universe has existed so far. So, how do helium white dwarfs exist today? The answer is binary star systems. If a star is in a close binary orbit with a companion, the companion's gravity can strip away the star's outer hydrogen layers before the core ever reaches helium ignition temperatures. The stripped core, now exposed, becomes a helium white dwarf. These objects are less massive than typical carbon-oxygen white dwarfs, usually below about half a solar mass. They're less common, but they exist, and they tell us interesting things about stellar interactions in binary systems. At the high end of the mass range, the most massive white dwarfs can have cores composed of oxygen and neon instead of carbon and oxygen. These oxygen-neon white dwarfs form from stars that were massive enough to ignite carbon fusion in their cores, but not massive enough to proceed all the way through the full sequence of nuclear burning that leads to iron cores and supernova explosions. Stars in this transitional mass range, roughly between about 8 and 10 solar masses, can fuse carbon into neon and heavier elements like sodium and magnesium, leaving a core composed primarily of the oxygen already present from helium burning, along with the newly produced neon. But when the carbon is exhausted, the temperatures aren't high enough to fuse oxygen or neon. The core, now composed of oxygen and neon, becomes degenerate and is eventually revealed as a white dwarf when the star ejects its outer layers. Oxygen neon white dwarfs tend to be more massive than their carbon-oxygen cousins, typically near the Chandrasekhar limit. They're rarer because the mass range of progenitor stars that produce them is narrow, but they're astrophysically important because their proximity to the Chandrasekhar limit means they're closer to the edge of stability. A little extra mass from a companion star could push them over the limit with dramatic consequences. Regardless of the exact composition, all white dwarf cores share certain fundamental properties. They're degenerate. The electrons provide the support pressure. The nuclei form a dense lattice or liquid depending on the temperature. And critically, there is no sustained nuclear fusion happening anywhere in the core. This is one of the most important distinctions between a white dwarf and an ordinary star, and it's worth dwelling on because it changes everything about how the object behaves. In a main sequence star like the Sun, the core is a nuclear furnace. Hydrogen is being fused into helium at a rate of hundreds of millions of tons per second. This fusion generates an enormous flow of energy that works its way outward through the star over the course of hundreds of thousands of years. The energy drives convection in certain layers, it creates radiation pressure, it heats the gas, and ultimately, it's what makes the star shine. The core of a main sequence star is dynamic. It's churning, burning, converting mass into energy. It's alive in a physical sense. The core of a white dwarf is nothing like this. There's no fusion, no energy generation, no conversion of mass into energy. The carbon and oxygen nuclei just sit there in their lattice positions, vibrating gently from residual thermal energy, but not reacting, not fusing, not doing anything chemically or nuclearly active. The core is static, frozen in the sense that no transformative processes are occurring, even if the temperature is still high by everyday standards. In a normal star, energy flows outward from the core through several mechanisms. In the inner regions, energy is transported by radiation, individual photons bouncing from particle to particle, slowly working their way outward. In the outer regions of many stars, convection takes over. Hot gas rises toward the surface, cools, and sinks back down, carrying energy outward in bulk. These processes create complex dynamics within the star. Convection zones churn and bubble, radiation zones are more stable but still involve an enormous flow of photons. The star is a dynamic system with energy flowing through it constantly. A white dwarf's energy transport is much simpler. There's no fusion-generated energy flowing outward from the core. The only energy being radiated is the residual thermal energy stored in the nuclei and the degenerate electrons from when the white dwarf was first formed. This stored heat slowly conducts outward through the degenerate core. The degenerate electrons are actually extremely good thermal conductors because they're free to move throughout the interior and they can carry thermal energy very efficiently. As a result, the core of a white dwarf is nearly isothermal, meaning it has almost the same temperature throughout its entire volume. The temperature might vary by only a few percent from the center to the edge of the degenerate core. This is radically different from a normal star. In the Sun, the core temperature is about 27 million degrees, while the surface temperature is about 10,000 degrees. There's an enormous temperature gradient from inside to outside. In a white dwarf, the core might be at 10 million degrees throughout almost its entire degenerate volume, with the temperature only dropping significantly in the thin, non-degenerate envelope near the surface. The envelope acts as an insulating layer, a bottleneck that controls the rate at which heat escapes from the interior. The degenerate core can conduct heat efficiently within itself, but the heat gets trapped at the boundary between the degenerate core and the non-degenerate envelope. It seeps through the envelope slowly, reaches the surface, and is radiated away into space. This is why white dwarfs cool so slowly. The core has an enormous amount of stored thermal energy, and the envelope lets it out only gradually. There is also no radiation pressure inside a white dwarf, at least not in the way that exists inside a normal star. In a main sequence star, photons generated by fusion reactions exert an outward pressure as they stream through the stellar interior. This radiation pressure contributes to supporting the star against gravity, especially in more massive stars, where it can be the dominant support mechanism. But in a white dwarf, there are no fusion-generated photons streaming outward. The radiation field inside the white dwarf is in thermal equilibrium with the matter, not being driven by an energy source. Any radiation pressure that exists is negligible compared to the electron degeneracy pressure. The white dwarf is supported almost entirely by degeneracy pressure, with thermal pressure and radiation pressure playing only minor roles that become even less significant as the white dwarf cools. This absence of active energy generation also means there are no magnetically driven dynamo processes of the kind found in many active stars. The Sun's magnetic field is generated by the motion of electrically conducting plasma in its convection zone, where rising and falling currents of hot gas create electrical currents that generate magnetic fields. This process, called a dynamo, requires convective motion driven by energy flowing outward from the core. A white dwarf doesn't have this kind of convection-driven dynamo. Yet some white dwarfs do have powerful magnetic fields, some exceeding 1 billion Gauss, compared to the Sun's average field of about 1 Gauss. Where these fields come from is still debated. They might be fossil fields, remnants of the magnetic field the star had during its active life, compressed and amplified by the collapse of the core. Or they might be generated during the white dwarf formation process itself. Whatever their origin, they're not being sustained by any ongoing dynamo process. They're just there, frozen into the structure of the white dwarf, slowly decaying over cosmic timescales. So let's assemble the complete picture. From the outside in, a white dwarf consists of a thin atmosphere, perhaps a few hundred meters thick, composed of hydrogen or, in some cases, helium. Below that is a non-degenerate envelope, a layer of gas that behaves more or less normally, extending perhaps a few hundred kilometers inward. This envelope contains residual hydrogen and helium and acts as an insulating blanket controlling the rate of cooling. Below the envelope is the degenerate core, which comprises more than 99% of the white dwarf's mass. This core is composed of bare carbon and oxygen nuclei, fully ionized, immersed in a dense sea of degenerate electrons. In a young, hot white dwarf, the core nuclei are in a liquid-like state, moving freely through the electron sea. As the white dwarf cools over billions of years, the nuclei in the center begin to crystallize, forming an orderly lattice that grows outward over time. The degenerate electrons fill the spaces between the nuclei, moving freely throughout the lattice, providing the degeneracy pressure that supports the entire structure against gravity, and conducting heat efficiently across the core. There is no fusion, no energy generation, no convection driven by nuclear burning, no radiation pressure from streaming photons. The core is quiet, static, slowly cooling, slowly crystallizing, and incredibly stable. It is, in essence, the largest and most extreme crystal in the universe. A diamond the size of a planet. Except it's not really a diamond because it's made of fully ionized nuclei rather than bonded carbon atoms. But the analogy has a kernel of truth. In 2004, astronomers studying a white dwarf called BPM 37093, located about 50 light-years from Earth, determined that its core had likely crystallized into a structure dominated by carbon. This prompted headlines describing it as a diamond star, a cosmic diamond 10 billion trillion carats in size. The description is poetic rather than precise, but the underlying science is real. The cores of old, cool white dwarfs are indeed crystalline structures composed largely of carbon. This is what's inside a white dwarf, not a featureless ball of compressed gas, not a simple solid sphere, but a layered, structured object with a thin atmosphere, an insulating envelope, and a vast crystalline core of carbon and oxygen nuclei, bathed in a sea of quantum mechanical electrons. An object that is simultaneously dead and enduring, static and magnificent, simple in its composition, and extraordinary in its physics. Every white dwarf in the galaxy contains this structure. Every one of them is a slowly cooling crystal of stellar ash, held together by gravity and held up by quantum mechanics, radiating away the last traces of heat from a fire that went out millions or billions of years ago. They are the most patient objects in the universe, sitting quietly in the darkness of space, glowing ever more faintly as the eons pass, their crystalline hearts growing one layer at a time as the temperature drops degree by degree across timescales that dwarf the current age of the cosmos. We've now explored what a white dwarf is made of, how it's structured, and what holds it up. But to truly understand what a white dwarf is, you need to understand what it isn't. You need to see the boundary, the line where the physics of a white dwarf ends and something entirely different begins. Because the white dwarf exists in a very specific range of conditions. It occupies a precise niche in the landscape of possible objects. Below a certain mass, it's stable, permanent, supported by electron degeneracy pressure for timescales that stretch into the trillions of years. But above a certain mass, at or beyond the Chandrasekhar limit of approximately 1.4 solar masses, everything changes. The electron degeneracy pressure that so faithfully held up the white dwarf fails. And what happens next is one of the most violent and dramatic transitions in all of astrophysics. The matter doesn't just compress a little more, it undergoes a complete transformation. The very identity of the particles changes. Electrons and protons cease to exist as separate entities. They're crushed together, merged into neutrons. The crystalline lattice of carbon and oxygen nuclei, that elegant structure of bare nuclei suspended in a degenerate electron sea, is annihilated, destroyed completely, replaced by something denser, stranger, and far more extreme. The object that emerges from this catastrophic collapse is a neutron star. And understanding the difference between what happens inside a white dwarf and what happens inside a neutron star is one of the clearest ways to appreciate just how remarkable and how fragile the white dwarf's equilibrium really is. Let's walk through what actually happens at the boundary. Imagine a white dwarf in a binary star system. It's orbiting close to a companion star, a normal star that's still burning hydrogen and expanding as it ages. As the companion swells, its outer layers begin to overflow toward the white dwarf. Matter streams from the companion onto the white dwarf's surface, accumulating layer by layer. The white dwarf grows more massive. With each bit of added mass, the gravitational compression increases. The electrons in the interior are squeezed into higher and higher energy states. The degeneracy pressure rises to compensate. But as we discussed, there's a limit. As the electrons are forced to move faster and faster, they approach the speed of light. And when they become relativistic, the degeneracy pressure can no longer increase fast enough to keep up with the growing gravitational force. The white dwarf approaches the Chandrasekhar limit. What happens when the limit is reached depends on the composition of the white dwarf. For a carbon-oxygen white dwarf, the most common type, something spectacular occurs before the collapse can proceed to completion. As the density and temperature in the core increase from the added mass, the carbon nuclei find themselves in conditions where they can finally begin to fuse. Remember, the original star couldn't reach the temperatures needed for carbon fusion. But now, with the additional gravitational compression from the accreted mass, the conditions change. Carbon ignites. But this isn't the controlled, gradual fusion that occurs in a normal star. In a normal star, if fusion speeds up, the star expands slightly, which cools the core, which slows the fusion down again. There's a self-regulating feedback loop. In a white dwarf, this feedback doesn't work. The white dwarf is supported by degeneracy pressure, which doesn't depend on temperature, so when the carbon ignites and the temperature rises, the white dwarf doesn't expand to compensate. The temperature keeps rising, the fusion accelerates, the rising temperature makes the fusion faster, which raises the temperature more, which makes the fusion even faster. It's a thermonuclear runaway. Within seconds, the fusion rips through the entire white dwarf. The energy released is so enormous that it completely unbinds the star. The white dwarf is blown apart in a titanic explosion. Nothing remains. No core, no remnant, no neutron star. The entire object is converted into energy and fast-moving debris. This is a type Ia supernova, one of the most powerful explosions in the universe. For a brief period, a single exploding white dwarf can outshine an entire galaxy containing hundreds of billions of stars. Type Ia supernovae are critically important in astronomy because they all have roughly the same peak brightness. Since they all involve the destruction of a white dwarf near the Chandrasekhar limit, and since the Chandrasekhar limit is a fixed physical constant, the explosions are remarkably uniform. This makes them excellent standard candles, objects whose known intrinsic brightness allows astronomers to calculate distances. It was observations of type Ia supernovae in distant galaxies in the late 1990s that led to the discovery that the expansion of the universe is accelerating, driven by the mysterious force called dark energy. Two teams of astronomers, the Supernova Cosmology Project and the High Z Supernova Search Team, independently measured the distances to distant type Ia supernovae and found they were farther away than expected. The universe wasn't just expanding, the expansion was speeding up. This discovery won the 2011 Nobel Prize in Physics, and it all traced back to exploding white dwarfs. But the type Ia supernova pathway is not the only possibility. For oxygen neon white dwarfs, which are already closer to the Chandrasekhar limit and have different fusion properties, the story can unfold differently. In these objects, instead of a thermonuclear runaway that destroys the star, the collapse can proceed all the way through. The electrons are forced into protons through a process called electron capture. This is a quantum mechanical process where a high-energy electron collides with a proton in a nucleus, and the two merge to form a neutron, releasing a neutrino in the process. The equation is straightforward. An electron plus a proton yields a neutron plus a neutrino. The neutrino, being an extremely weakly interacting particle, escapes immediately, carrying away energy. The neutron remains behind. As electron capture proceeds, something devastating happens to the white dwarf's support structure. Every time an electron merges with a proton, there is one fewer free electron in the system. The number of degenerate electrons decreases. And since it's those electrons that are providing the degeneracy pressure holding the white dwarf up, the support weakens. Gravity gains the upper hand. The matter compresses further, which increases the density and temperature, which accelerates the rate of electron capture, which removes more electrons, which weakens the pressure further. It's a catastrophic feedback loop. The support structure of the white dwarf is being dismantled from within. Electron by electron, the quantum floor is being pulled out from under the object. The collapse is not gentle. Once it begins in earnest, it happens incredibly fast. The core of the white dwarf, which had been sitting in equilibrium for perhaps billions of years, collapses in a fraction of a second. The matter compresses by a factor of roughly 100 million in density. Material that was at 1 million grams per cubic centimeter is driven to hundreds of trillions of grams per cubic centimeter. The entire carbon-oxygen or oxygen-neon lattice is destroyed. The individual nuclei are crushed together. The distinct carbon and oxygen nuclei, which had maintained their identity throughout the entire life of the white dwarf, are broken apart. Protons and neutrons are liberated from the nuclei and reform into a dense sea of neutrons. What emerges from this collapse is fundamentally different from a white dwarf. It's a neutron star, and the differences between the interior of a white dwarf and the interior of a neutron star are so vast that they're almost different categories of existence. Let's compare them directly. A white dwarf has a density of roughly 1 million grams per cubic centimeter. A neutron star has a density of roughly a few 100 trillion grams per cubic centimeter at its core. That's a difference of roughly 100 million times. If white dwarf material is unimaginably dense, neutron star material is unimaginably denser still by a factor that itself is almost impossible to comprehend. A white dwarf has a radius of roughly 6,000 kilometers, similar to Earth. A neutron star has a radius of roughly 10 to 12 kilometers, the size of a city. All the mass of the star, 1.4 solar masses or more, compressed into a sphere about 12 kilometers across. If a white dwarf is the size of Earth, a neutron star is the size of Manhattan. The size difference alone tells you how much more extreme the compression is. In a white dwarf, the matter consists of distinct atomic nuclei, carbon nuclei, oxygen nuclei, sitting in a lattice or liquid state surrounded by degenerate electrons. The nuclei are intact. They maintain their identity as carbon or oxygen. They have structure, protons and neutrons bound together by the strong nuclear force. They're separated from each other by gaps filled with the electron sea. In a neutron star, none of this structure exists. The individual nuclei have been destroyed. The protons and neutrons that made up those nuclei have been liberated, and most of the protons have been converted into neutrons through electron capture. What you have is a sea of neutrons with a small admixture of protons and electrons. There are no distinct nuclei, no lattice, no crystalline structure in the bulk of the interior. The matter has been homogenized into a uniform neutron fluid. In a white dwarf, the support comes from electron degeneracy pressure. The Pauli exclusion principle applies to electrons. In a neutron star, the support comes from neutron degeneracy pressure. The Pauli exclusion principle applied to neutrons, along with the strong nuclear force, which provides an additional repulsive component at very short range. Neutrons, like electrons, are fermions. They obey the Pauli exclusion principle. Two neutrons cannot occupy the same quantum state. So when neutrons are compressed together, the same kind of degeneracy pressure arises as with electrons. But because neutrons are about 2,000 times more massive than electrons, the conditions required to reach degeneracy are far more extreme. You need far higher densities, and that's exactly what you get in a neutron star. The physics governing the interior of a neutron star is fundamentally different from the physics governing a white dwarf. A white dwarf is governed primarily by quantum electrodynamics, the interaction between charged particles and electromagnetic fields. The electrons interact with each other and with the nuclei through electromagnetic forces. The degeneracy pressure is an electron phenomenon. The crystal lattice forms because of electromagnetic repulsion between nuclei screened by the electron sea. It's all electromagnetism and quantum mechanics at the level of electrons. A neutron star is governed by nuclear physics and quantum chromodynamics. The physics of the strong force that binds quarks together inside protons and neutrons. The strong force operates at distances comparable to the size of an atomic nucleus, roughly 1 quadrillionth of a meter. At the densities found in a neutron star, particles are compressed to these separations, and the strong force becomes the dominant interaction. The physics shifts from the realm of electrons and electromagnetic forces to the realm of neutrons, nuclear interactions, and potentially even quark matter at the highest densities found in the core. The surface and crust of a neutron star do have some similarities to a white dwarf. The outermost layers contain ordinary nuclei, iron and other heavy elements, arranged in a crystal lattice much like the core of a white dwarf. But as you descend through the crust, the pressure increases, and the nuclei become more and more neutron-rich. Nuclei that would be highly unstable under normal conditions. Nuclei with far more neutrons than protons become stable under the immense pressure. At a certain depth, called the neutron drip line, the nuclei can hold no more neutrons. Free neutrons begin to leak out of the nuclei, forming a sea of neutrons that coexist with the remaining nuclei. This is the inner crust, a bizarre region where neutron-rich nuclei float in a sea of free neutrons. Deeper still, the nuclei dissolve entirely, and you enter the outer core, which is a uniform fluid of neutrons, protons, electrons, and possibly muons. The neutrons in this region are thought to form a superfluid, a quantum state of matter, where the fluid flows with zero viscosity, and the protons may form a superconductor, a state where electrical current flows with zero resistance. These are quantum phenomena that we associate with ultra-cold laboratory experiments on Earth, occurring at temperatures near absolute zero. But in a neutron star, they occur at temperatures of millions of degrees, because the density is so extreme that quantum effects dominate even at high temperatures. At the very center of a neutron star, in the inner core, the density may exceed several times the density of an atomic nucleus. At these densities, our understanding of physics becomes uncertain. The neutrons might break apart into their constituent quarks, forming a quark-gluon plasma, or they might form exotic states of matter like kaon condensates or hyperon matter, particles containing strange quarks that don't exist in ordinary matter. No one knows for certain because we can't recreate these conditions in any laboratory on Earth. The core of a neutron star probes physics at the absolute frontier of human knowledge. None of this exists inside a white dwarf. The white dwarf's core is comparatively simple. Familiar elements, carbon and oxygen, in a crystalline lattice, supported by well-understood electron degeneracy pressure. The physics is exotic compared to everyday life, certainly, but it's well within the bounds of established quantum mechanics and electrodynamics. A neutron star's interior, by contrast, pushes into territory where our theories become uncertain, and our predictions become tentative. The white dwarf is the last stop where physics as we know it still holds firm. Beyond it, past the Chandrasekhar limit, we enter a realm of increasingly exotic and poorly understood matter. This contrast also highlights something important about the Chandrasekhar limit itself. It's not just a number, it's a boundary between two fundamentally different states of matter. Below the limit, matter can exist as electron-degenerate material. Above it, matter is forced into a completely different configuration. The transition is not gradual, it's not a smooth slide from one state to another. It's a catastrophic collapse, a violent transformation where the very nature of the particles changes. Electrons and protons cease to exist as separate entities and merge into neutrons. The crystalline lattice of nuclei is obliterated. The density jumps by a factor of 100 trillion. Everything changes. The Chandrasekhar limit is a cliff edge in the landscape of possible objects, and falling off that edge means entering an entirely different world of physics. Now, let's turn to the other end of the white dwarf story. Not its catastrophic death if pushed past the Chandrasekhar limit, but its quiet fate if left undisturbed. Because most white dwarfs will never accrete enough mass to reach the limit. Most of them are solitary objects or members of wide binary systems where mass transfer doesn't occur. They'll simply sit in space, cooling, for an almost unimaginable length of time. We've already discussed how white dwarfs cool. They radiate away their stored thermal energy through their thin insulating envelopes. The cooling is slow because the envelope restricts the flow of heat and because the core contains an enormous reservoir of thermal energy. A newly formed white dwarf might have a surface temperature of over 180,000 degrees Fahrenheit, glowing a brilliant blue-white. Over hundreds of millions of years, it cools and dims, passing through white, then yellow, then orange, then red. The surface temperature drops from tens of thousands of degrees to just a few thousand degrees Fahrenheit over billions of years. But here's what's remarkable. Even after the white dwarf has cooled significantly, even after billions of years, it still has degeneracy pressure holding it up. The cooling doesn't affect the support mechanism at all. The white dwarf gets dimmer and cooler, but it doesn't get smaller or less stable. Its structure remains the same. The crystalline core continues to grow as the temperature drops, and the surface grows fainter and fainter. but the object persists, unchanged in size, unchanged in mass, unchanged in its fundamental structure, just cooler and darker. The theoretical endpoint of this cooling process is something called a black dwarf. A black dwarf would be a white dwarf that has cooled so completely that it no longer emits any significant light or heat. It would be a dark, cold, crystalline sphere of carbon and oxygen, invisible against the blackness of space, detectable only by its gravitational effects. A stellar corpse that has finally gone completely cold. But here's the extraordinary thing. No black dwarfs exist, not one, anywhere in the universe. The reason is simple. The universe isn't old enough. The cooling process is so slow that even the oldest white dwarfs in the universe, those that formed from the very first generation of stars that died billions of years ago, are still glowing. They've dimmed enormously. The oldest known white dwarfs have surface temperatures of around 5,000 to 7,000 degrees Fahrenheit, cooler than the sun, but still warm enough to emit visible light, a dim reddish glow. But they haven't gone dark yet. They still shine. Estimates suggest that a white dwarf would need at least a quadrillion years to cool to the point where it emits essentially no radiation. A quadrillion is a 1 followed by 15 zeros. The exact number depends on the white dwarf's mass, composition, and the properties of its envelope, and some estimates push the timescale to 100 quadrillion years, or even longer. The universe is only 13.8 billion years old. Even a single quadrillion years is more than 70,000 times the current age of the cosmos. We are not even remotely close to the era when black dwarfs will exist, and even then, the white dwarfs would still be structurally intact, still supported by electron degeneracy pressure, still crystalline, still the same size they were when they first formed, just cold and dark. This means that white dwarfs will outlast essentially everything else in the universe. They will outlast main sequence stars, because those will eventually exhaust their fuel and die. They will outlast red dwarfs, the longest-lived stars, which will burn for trillions of years, but eventually run out of hydrogen. They will outlast galaxies as coherent structures, because over sufficiently long timescales, gravitational interactions will eject stars from galaxies, dissolving them. In the far, far future, when the last stars have burned out and the galaxies have dispersed, white dwarfs will still be there. Dark, cold, invisible, but present. Floating through the void as black dwarfs, crystalline monuments to stars that once burned. On even longer timescales, far beyond anything we can practically contemplate, even the matter in black dwarfs might decay. Some theories predict that protons are unstable and will eventually decay into lighter particles. If proton decay occurs, which remains unproven, it would happen on timescales of roughly 10 to the power of 40 years or longer. This is a number so vast that it makes the current age of the universe look like literally nothing. But if proton decay does occur, then over these incomprehensible timescales, the carbon and oxygen nuclei in the black dwarf's core would slowly disintegrate. The protons within those nuclei would decay one by one, converting into positrons and neutral pions, which would quickly decay further into photons. The positrons would annihilate with electrons, producing more photons. Gradually, the mass of the remnant would be converted entirely into radiation. Gradually, over timescales that defy human language, the black dwarf would evaporate. Eventually, nothing would remain. The final trace of a star that once burned would dissolve into light. The final dissolution of the last stellar remnant. But this process, if it occurs at all, is so far in the future that it barely connects to anything we understand as time. What we're left with, when we step back and consider the full picture, is this. A white dwarf is matter in suspension. Dead stellar material, the carbon and oxygen ash of nuclear fusion, compressed to extraordinary density and held in that compressed state by a quantum mechanical rule about how electrons behave. It is not alive. It generates no energy. It performs no chemical or nuclear reactions. It's the most inert macroscopic object in the universe, just sitting there, doing nothing except slowly radiating away the heat it was born with. And yet, it endures. Not for millions of years, not for billions, for trillions, potentially for quadrillions, longer than any star will burn, longer than any galaxy will hold together. The white dwarf is the universe's most patient object. It waits, and waits, and waits, cooling by fractions of a degree over billions of years, growing its crystal core one layer at a time, dimming so slowly that the change would be imperceptible over the entire span of human civilization. And through all of that waiting, the electron degeneracy pressure never falters, never weakens, never needs to be refreshed or renewed. It simply exists. A consequence of quantum mechanics, holding the object in its compressed state against gravity with the same strength it had the day the star died. There is something deeply moving about this when you think about it carefully. Every white dwarf in the sky was once a star. It was once a brilliant, luminous object pouring energy into space, lighting up its corner of the galaxy, possibly warming planets where life might have existed. It burned for billions of years, fusing hydrogen into helium, helium into carbon, carbon into oxygen. It was dynamic, active, alive in every physical sense of the word. And then it died. The fuel ran out. The fire went cold. The outer layers drifted away into space, forming a beautiful but temporary nebula that dispersed after a few tens of thousands of years. And what was left behind was this small, dense, quiet thing. A white dwarf. The ashes of a star. The embers of a fire that went out. But those embers don't fade to nothing. They persist. They endure across cosmic timescales that dwarf anything else in the universe. The star's active life, brilliant as it was, lasted perhaps 10 billion years. Its afterlife as a white dwarf will last 1,000 times longer. The burning was the brief part. The quiet persistence is the long part. The star's greatest achievement wasn't the light it produced during its active life. It was the structure it left behind when the light went out. A structure so perfectly balanced, so precisely engineered by the laws of physics, that it will outlast virtually everything else in the cosmos. Every white dwarf you could observe through a telescope tonight was once a star like the Sun, or smaller. Some were stars that might have had planets. Some of those planets might have had oceans, atmospheres, weather. Some might even have had life. All of that is gone now. The planets might still be there, orbiting the white dwarf in the darkness, but they're frozen, lifeless worlds circling a fading ember. The star that warmed them has become something else entirely. Something cold and dense and quiet. Something that will sit there in the darkness of space for trillions of years. A crystalline sphere of carbon and oxygen, glowing ever more faintly, remembering nothing of the light it once produced. All those tens of billions of remnants are out there in the Milky Way right now. Dead stars scattered throughout the galaxy like embers across the floor of a cold hearth. Each one containing roughly half the mass of a star, compressed into a volume the size of a planet. Each one supported by the Pauli exclusion principle, each one cooling toward an eventual darkness that won't arrive for trillions of years. Together, they represent the accumulated dead of the galaxy, the remnants of stars that lived and died over the 13 billion year history of the Milky Way, and they will be among the last things left when the galaxy itself is gone. When you look up at the night sky, you don't see them. White dwarfs are too faint to see with the naked eye, with only a handful of exceptions. They're invisible to casual observation, hidden among the bright points of light that are still living stars. But they're there, in vast numbers, silent, patient, enduring. They are the quiet majority of stellar endpoints. The vast majority of all the stars in the galaxy will end this way. Not as supernovae, not as neutron stars, not as black holes, as white dwarfs. Small, dense, crystalline remnants supported by a quantum mechanical pressure that asks for nothing and gives everything. That was once a star. The atoms in it were forged in the nuclear fires of stellar cores. The carbon in its interior was created by the triple alpha process, 3 helium nuclei combining under unimaginable heat and pressure. The oxygen was formed by carbon, capturing a 4th helium nucleus. These are the elements of life: carbon and oxygen, the building blocks of every living thing on Earth. And they're sitting inside every white dwarf, locked away in a crystalline prison of degenerate matter, unreachable, unusable, but present. The ingredients of life, trapped inside the corpse of a star, held in quantum suspension for trillions of years. This is what happens inside a white dwarf. Matter pushed to a state that exists nowhere else. Atoms destroyed and rebuilt into a degenerate plasma. Electrons obeying a quantum law that prevents collapse. Nuclei slowly forming a crystal that will outlast the stars. A dead object more enduring than anything alive. A remnant more permanent than the star that created it. The inside of a white dwarf is not just a curiosity of astrophysics. It's a profound demonstration of what matter can become when pushed to extremes. It shows us that the universe has states of existence far beyond our everyday experience. States where quantum mechanics rules, where the familiar categories of solid and liquid and gas lose their meaning, where matter can persist in compressed suspension for timescales that make the entire current age of the universe look brief. And it all comes down to one simple rule. 2 electrons cannot share the same quantum state. That's it. That single principle, discovered by a physicist in the 1920s, is what holds up billions of dead stars across the galaxy. It's what prevents them from collapsing further. It's what will keep them intact for trillions of years after the last living stars have gone dark. The inside of a white dwarf is a quantum mechanical masterpiece, a crystal made of stellar ash, supported by the stubbornness of electrons, enduring in silence across the longest timescales the universe will ever know. And every single one of them was once a star that burned. That is perhaps the most extraordinary thing of all.